You're already familiar with real numbers, the ones that fit neatly along the number line. Is it possible that there are other kinds of numbers that we haven't seen yet? Numbers that don't appear along that line? The question sounds odd, but strangely, that idea isn't strange at all. People have been inventing new kinds of numbers for a long time. One very familiar way to do that is to solve an equation like this one. The answer is not a whole number, an integer. It's a new and different kind of number. We call it a fraction, or rational number. A more famous example. The Greeks wanted to solve this problem about the length of the diagonal of a square. They did, by inventing irrational numbers. And they did that by defining a new symbol, square root, defined by what happens when we square it. And this is the idea we're going to copy for complex numbers. Our starting point is a little different. The equation we want to solve looks like this. It doesn't look difficult, but it turns out that x cannot be a real number. Why not? Because here, x squared equals a -1. And when you multiply a real number by itself, you get either 0 or a positive number. You never get a negative number. So what we need is a new symbol. And here it is, the symbol I. Its defining property, the square of I is -1. So I equals the square root of -1. I is your first example of a complex number. More commonly, you'll find them looking like this. A and B are real numbers. The expression A plus BI is a complex number. Here are some examples. One curious fact is that all your real numbers are contained inside these new complex numbers. Here's an example of how to write the real number 5 as a complex number. Sometimes people label the two parts of a complex number as real and imaginary, but they're no more imaginary than the square root of 2 was. Now we want to find out how to work with these new numbers. Two complex numbers are equal if the real parts are equal and the so-called imaginary parts are equal. Now, how do you suppose we add two complex numbers? If we remove the parentheses, it might remind you of an old familiar friend, like terms. Can we add like terms here? Yes, we can. Combine the two real parts and combine the two imaginary parts. And our answer is still a complex number. It works. Subtraction, same thing. Gather like terms and see what you get. Try this one yourself and be careful with your negative signs. The first thing I do is remove the parentheses, being careful about negative signs. And collect the like terms. And after that, there's nothing left to do. My answer again is a complex number, 3 plus I. Next, multiplication, a real number times a complex number. You do it just as if you were using the distributive law with variables. 2 times 3 is 6, and 2 times 4i is 8i. Nothing to it. And multiplying two complex numbers together is almost as simple. Immediately you expect to use FOIL. And you're right. We multiply first, outside, inside, and last, and come up with 8 plus 10i minus 12i minus 15i squared, which does not look like a complex number because that 15i squared is something weird and different. Or is it? Surprise! I squared, remember, is exactly the same as negative 1. That's how we defined it in the first place. So, negative 15i squared is negative 15 times negative 1, or plain old positive 15. Add like terms, and we have 23 minus 2i, a complex number. Now here's one for you to do. First, I want to use FOIL to multiply out the brackets. That gives me an I squared term at the end, just like before. I use the same simple process, replace the I squared by negative 1, and then combine like terms, and I have my answer. And I hope you have my answer too. It's right. Here's an odd little problem. Watch what happens when we take the higher powers of I. We get a pattern that repeats every fourth power. If you're not convinced, figure out a few more on your own. It works. I and I to the fifth are the same. I squared and I to the sixth are the same, and so forth. And last of the algebra operations, there's division. We have to do something a bit different here. What we have to do is take the denominator, here it's 2 plus 3i, and define a new complex number called the conjugate. We do that by changing the sign in the middle. Here, change that plus to a minus. So the conjugate of our denominator is 2 minus 3i. Then we multiply both top and bottom by the conjugate. And if that reminds you of one of our methods of rationalizing square roots, well, it should. Here, our aim is to get our answer in the correct shape for a complex number. We finish the problem by using FOIL to multiply out both numerator and denominator. And once again, we have that I squared term at the end. So we turn I squared into a negative 1, multiply it out, and then gather like terms. The denominator turns into a real number. That was the whole point. And our answer again shows up as a complex number. What you need now is one to do on your own. And here you have it. First step, find the conjugate of the denominator and multiply by it, top and bottom, using FOIL. I find the conjugate by taking the denominator and rewriting it, changing the sign in the middle. I multiply top and bottom by the conjugate. Notice the two endings in I squared. Change the I squared to -1 and multiply. Combine like terms, and it's done. The material in this module has been rather strikingly new and different. You'll want to nail it down right away by doing some more problems in your textbook. What we've looked at in this module has been the algebra of complex numbers, a basic definition, and how to combine them. If you go beyond this course in math, you'll learn about the geometry of complex numbers. We can't place them on the one-dimensional real number line, but we can represent them exactly by pictures on the two-dimensional plane. We can also take their roots, and we'll discover a definite connection with angles as well. But all that will wait until later. Meanwhile, engineers in the electronics industry use complex numbers all the time in explaining circuits. And we'll soon put them to use in solving quadratic equations with the help of our old friend, the quadratic formula. And when we do, good luck.